This information is brought to you by Charles Sturt University.
Wait for them to come in.
Not many people here outside. Was there anyone?
Only two. They're taking the soft couches while I do it. Yeah. Hey guys. So what we're looking at the moment is Boolean algebras. So as I said yesterday, Boolean algebra is a pattern, essentially, and that pattern you see in many different areas. So the examples I listed off yesterday was sets and logic, the ones we've seen commonly, but it's also seen in sets of divisors and things like that. So it's a pattern you see commonly. And in order to verify that pattern is true, you need 5 basic properties, which I listed the other day, which is commutative, associative, distributive. So the identity laws for zeros and ones, and the last one was the complementary result. So those are the 5 basic results. Once you have those 5, then lots of other properties just follow from those. So once you match the pattern, then you've got lots of other results, like De Morgan's rule, for example, that comes free from that. And we've learned some of these already. We've seen them for sets and logic, but those apply in all situations. And so I want to show you how some of these other results follow from just the basic ones, essentially, to begin with, and then we'll look at how to use some of them. So the first of the sort of consequential results is the idempotent property. And so as long as you get the pattern, if you're going to know you've got the pattern, then this is automatically true. And so it's good to recognise something's a Boolean algebra because then you've got other results. So I want to try to prove these results by just using the 5 basic properties, essentially. So I'll just do one of them and go from there. So let's just start with x plus x. So basically what we want to do is we want to prove this is equal to x. And all we know are 5 basic rules. So the basic rules is commutative. Things like you can swap the order. It's one we know, and the same thing for the multiplication. We know associative. So if you're just summing up 3 in a row, you can do the first 2 or the last 2 first. Doesn't really matter. They're the same. It's the associative property. Distributive. Things like x plus y times z, you can distribute the sum or the multiplication over. That's the distributive property. The identity rules, things like x plus 0 equals x, x times 1 equals x, are the identity properties. And the last one is the complement ones. So x plus x bar equals 0, and x times x bar. That's all right. X plus x bar equals 1, and the product equals 0. So that's sort of basic properties we've got. So for the first few, they have, most of them, pretty much all these rules happen in pairs, if you haven't noticed yet. We'll talk more about it in a second. So I've only done the first, for the first 3, just do one of the pairs. So they're the 5 basic rules that we can sort of utilise. So I want to try to use them here. So, 1, mind's blank, but we'll work out what to do. So, what would we do? I don't know, I'm mucking around here. I'm going to add a 0 on there because I can. So what I'm trying to do is I'm trying to basically cancel out one of those x's effectively. That's what I'm going to try to do and see how I go. So in order to try to cancel anything using any of these rules, I really need to try to, pull some of these extra terms in. The only way I can do that is using a 0 to begin with. And I can add 0 whenever I want to. Next thing, the only other rule which I can really use, which I mentioned 0, is this bottom one here. So I just convert it to extra symbols. And the purpose of doing this is to try to group sort of things together, essentially. That's my hope, and see if I get anywhere with it. So I would like to factorise some of these things out. Am I getting anywhere with this? I saw it yesterday how to do it. Let me try that again. So I can just see I'm going around in circles. So if I multiply this by 1, so I get those products things happening, that's going to be equal to x plus x bar times by x plus x. So these, as you can work out, sometimes these really simple properties are hard to prove. Just work out which ones we're going to do. They get easier as we go. Okay, so I've tucked a 1 in there, so I can just add a 1 whenever I want to, etc. And then I'll replace the 1 by one of the rules I can. So my first attempt failed, as you've worked out. So I'm trying something different. And then what would I do next? What would you do next? Well, I would factorise out the x plus. So I can factorise out the x plus from this. And there's an x plus in both those terms. So I factorise it out to give me that sort of expression. That's the distributive property I'm using. So I'll just give some names. That's the identity. That's the complement. That's the distributive. And then what would you do next? So I want to try to simplify these equal to x. That's what I'm trying to go for.
X times not x equals 0.
Yeah. So this one, again, one of the complement results, kills to 0, and x plus 0 can be just simplified down to 0. X by itself is the identity. So my first approach failed, but I got it right the second time at least. So you can prove, that's the first result proved. Essentially, if you do x union or x or itself, you have to restart it from. And you could prove in a very similar fashion the other result, which I won't do. It is on the slides though. But I'll show you why you don't have to prove the other one a little bit later. I'll explain why I can only get away with just doing one. But that's one other property you can prove from what you've got there. Okay. So the other ones you can do are proving these special properties of zeros and ones. So let's just try to do the first one. So x, this, and again, if you're thinking in terms of logic, this is x and false. That's how you would translate it in that situation, or in terms of sets, be X intersection the empty set. And that 0 is strong, it sort of just cancels anything else out. That's sort of the idea. So I'm going to try to prove this is actually equal to 0. And we're going to try to utilise the result we've got. So now we've got 6 results. We have the item property as well as the first 5. So again, we've got to try to, in order to cancel things out, we really want to write down the 0 as something other sort of forms we know. So if you look at what you've got, the zeros we have available is that one really. So that's the first one I'll try. That's the one that stands out to me as it's got a 0 in it. So I'd write it as x times by x, x bar. And again, that's the complement property. We haven't seen much choice. Then I go, that's similar to one of the results I had a second ago. So I'm just going to rewrite the brackets. That's the associative property. And what's x dot x? So it's x and x essentially.
X on its own. X on its own.
X on its own, that's right. And that's that idempotent property we just looked at. So idempotent means it's its own power. So if you just do it to itself, you get back to where you started from. And what's x and not x?
0.
Then 0. Or the complement. So as you can see, in order to prove that one, we use the idempotent property we did in the last slide. So these sort of results build up from themselves. So Mr. Bull, or I just think his name's George, but anyway, whatever his real name is, he worked out that you can work at the simplified set of the rules, and you can extend from that. People have worked out what possible minimum rules they can be too. They've done lots of things with them. So as you can tell, you keep building them up. So let's try to the absorption properties. So x and x plus y. Again, in terms of a picture, in terms of visually what we're trying to do here. So think in terms of sets. If you've got the first one is the union. So you've got the union of two sets, and you're trying to do it. So you've got the whole union. This is like A union B. That corresponds to the x plus y. If we then take the intersection of that with the first one, we're just going to pull back. We're just going to get what we're just going to get the A set again. So it's pretty much saying that if you've got A intersection a union, you just get the A out. And the second one is if you've got A union with an intersection, which is completely contained in it, you just get the big set. So essentially, what's happening in terms of the bottom rule, that term is absorbed in the x. Put another way, this term here is absorbed in the x. It's the absorbed. So in terms of the rules I gave at the beginning of the session, in terms of sets and logic, this was not one of the basic rules that I presented. We did prove it in terms of sets along at the very beginning of the session. So maybe week 1 or 2, can't remember anymore. And we proved, the way of proving it is essentially the same way here, that is realising just using the basic rules. So the way we proved it back then, involving the rules of sets, is really using the rules of Boolean algebra. That same property is true for all Boolean algebra. Now the challenge is to try to work out how to prove it, essentially. So I'll pick one of them. And then we've got to try to work out how to do it. So, any ideas? One option, that seemed like a good idea the first time, it doesn't help straight away though, is to go, let's just expand the brackets. So let's just do the distributive property. So it'll be x and x plus x and y. That's just distributive property. What does that simplify down to?
X plus x or y.
Yep.
Y.
And if you notice, that's the other term. So you can see that they're really closely related to each other. So that's not really helping yet. least we can do them both at the same time effectively. So how are we going to try to do it? So cheat. Let's put an x plus 0 in here. Is that going to work? Not really. So how does it work? I mean, essentially what it's based upon is knowing that is the basic rule, if you've got 1 and anything, you get 1. It's really just a specialised case of that rule. That's what it really corresponds to. Is 1 absorbing anything else. That's the ultimate in terms of absorption. So we want to try to utilise that result somehow, actually. So
I don't know how you do it. Like, I don't know how you do it with the rules or whatever. But you can see that anything or itself and something else has to be itself on its own.
yeah,
Like,
yeah. In terms of if you draw a Venn diagram, straightforward, right?
makes sense. It's just how do you write it?
You could just go trial and error. You just run, when x equals 1 and y equals 1. You just run through all the things. Easy peasy.
So if you've got a truth tables,
Yep.
you just do a truth table, Venn diagram. So they just prove it for particular instances of Boolean algebras.
If you did it for every instance,
There's an infinite number of them.
but there isn't.
Huh?
Like, there's only a few things that you can put in, ones and zeros.
Trues and false, threes and fours, reds and blues, green and yellows.
Yes, but
So
they're
any-
obviously going to be only 2 options.
Yeah, I
Therefore, you
know.
can apply it to all of them.
And that's the thing about Boolean algebras. It's just two.
There's only 2 things, exactly. There's not infinite.
You got a true and a false essentially.
So the Boolean algebras, they don't necessarily just have to have 2 options. So an example of a Boolean algebra is a set of all finite sets and cofinite sets.
It's 2 things.
No. So say you've got the set of integers, then how many finite sets of integers are there? Lots of them. An infinite number even, an uncountable number of them.
I want to count them
And then you have cofinite. Cofinite means all sets which have all elements except with a finite number of deleted. It's a cofinite set. Again, that'd be an uncountable number of them. So you can have uncountable Boolean algebras. And essentially, the results would behave the same way. They're just simply just sets. And so the rules, you can still use a Venn diagram to prove it in that case. But we've got to try to prove all situations. So, mind blank here. Really mind blank, sorry.
Big formula sheet for this subject.
Go.
What are the big formula sheet for this subject?
Sorry that I just can't remember how to do it. It's terrible, really. I prepared yesterday these things, and I could do it all yesterday. Yesterday. As it goes.
Does it have anything to the fact that it's like 9:20 in the morning?
Oh, shouldn't
Or
be.
12. Or 12.
That's the terrible excuse.
Way too early.
Do you know what time is your exam?
9:20 in the morning.
Okay.
Ooh. It's for 3 hours, hey?
I was making a point, Michael. That was the idea.
For 3 hours.
All right, you can do this sort of question at the end of the exam. If you
You
want.
mean we're going to have to prove one of these things in the exam?
Yep.
Oh, now he's got to tell every student.
So yes, things I expect to know for Boolean algebras. I expect to know that there are a variety of different
That is actually not.
implementations of it, instantations of it. So that's one thing, which is what we did yesterday afternoon.
Taking that for an hour.
You know, to prove some things with it,
Fine.
which is not surprising. We've been able to prove some things for a while now, and especially about to simplify expressions, which I'll get to in a little bit. So as I said, so let's just go through the lines. So name the rules as we go through. So the first one is the identity property. So just tracking your one on whenever you feel like it. Then that the whole thing this is based around is that absorption property of one. That's how this is what the rule's really based on. Just a special case for that. So that one absorbs anything, so you can just chuck the y on when if you like it. And then you can expand the brackets, so distribute over the products. And then the one, x times 1 is just the identity property again, which gives you that first rule and the last two steps I did already on the slide. So as I said, although I can't remember how I proved it, it really is that based on that absorption property of 1. Okay, idea. And if I kept remembering that, I eventually recall how to prove it, but you'll have to trust me.
But if you read up, you can get the proof for that. From bottom to top.
Yes, I guess so. Okay, let's see if I can not stuff up this one.
Place my bets.
Do it quietly.
Anyone else want to place a bet? Paul?
Okay, so what this one's trying to say, and this is an important little tool here, is that basically there are two rules involving complements, and that is x plus x bar equals 1 and x times x bar equals 0. So what this is, so that's the defining rule for a complement, essentially what they do. So they're the two defining properties for it. So what this is trying to say is if you can find anything else which satisfies those two same rules, then it happens to be the complement. So essentially, this idea of a complement is unique. I mean, once you satisfy both those rules, that's it. That is the complement. And so knowing what the purpose of that rule is then, in order to prove anything else is a complement, all it just involves around proving those two rules. That's what we have to do. So we can prove those two results here, or effectively these ones, the same thing really, then that proves it's a complement. That's how you prove complement stuff. And if you remember trying to prove De Morgan's law at the beginning of the session, I did that in lectures. It was a bit hard to understand because I was trying to do it all in one go. It's easier to prove it using just those two steps there. That's much a clearer proof for it. Which we'll do in a second with De Morgan. So let's try to prove these things. So essentially I want to prove that U is equal to A bar. That's what I'm trying to prove. So I know that got these two rules, effectively sort of complement sort of stuff. So I can always chuck a 0 on whenever I feel like. So what I'm trying to do is I'm trying to add stuff along, and they just start killing the U's but leave the A bar behind. That's the basic idea. So 0 is equal to A plus A bar. That's one of the first complementary results. That's what I'm really trying to do, just trying to use the complementary result. Now, being associative, I can do it I can expand any order I want to, but I know that this U plus A here let's write down the correct stuff here, shall I? Maybe that'll be better.
Thank you. Very lost that for a second.
Okay. What do I do next? I'm not very well today, am I? I would expand this thing out. So I've got U plus A times by U plus A bar. What's the U plus A? 1. That's sort of what we're assuming here. And then, so basically I've got to the middle position, I've got the sum of the two. And now I want to sort of go backwards, heading towards A bar. So I'll sort of just undo all my steps. So instead of with the 1, I expand it now as A bar plus A. So I really am just going backwards, essentially, just doing the same sort of step, but just replacing the U's by A bars this time. Then it's worthwhile just reordering it just so I can see what I'm doing better. So it's A bar plus A times by A bar plus U. And why am I allowed to do that?
I feel like
You're just reordering the same.
yeah, you literally just,
All I do is change the order, and I'm allowed to do that because of commutative property. So I'm allowed to reorder things when I feel like it. That's commutative property. And then what would I do next? So I said I'm really just doing these first few steps here in the opposite order. That's what I'm really doing, just replacing A bars and U. So I've got from U, made it more complicated, and now I'm simplifying it down. And I want to simplify it down to A bar. So what I did in this case, going forwards, is I basically expand the brackets. So I'm going to do the opposite here. I want to factorise. So I'm factorising this A bar out. That's what I'm factorising out, the A bar plus. And what's the A dot U equal to? 0. And adding 0 to anything just gives you the original thing back again. So in terms of my proof structure here, is I started with U, I want to finish with A bar. So I wanted to blow it up a bit, essentially, and blow it up in a bit. And in the middle here, as you can see, the middle step is really just the sum of the two. So I've just added a few things on, so I've eventually got a plus A bar, and I do exactly the same sort of steps to get rid of the U in exactly the way I added the A bar in the first place. So it's a symmetrical proof in this case. So the implication is more important than anything else. And that is, if you want to prove something's a complement of another element, really revolves around proving these two results are true. So, as an application of that, we can see that by symmetry, x bar plus x equals 1 and x bar dot x equals 0, and that's automatically true, right? Just swap the orders. So that implies then that the complement of the complement must be equal to x. So because x satisfies the results being a complement of x bar, that means the double complement is actually equal to x. That essentially proves that result. So that's one of the special results of the double complement is the original value again. And that's one of the very few rules that don't come in pairs. But you can also use that sort of idea for De Morgan's rule. De Morgan's law, which is the next one I'm going to do. So what is De Morgan's law? You remember? So De Morgan's law is basically a way of simplifying the not of an and or an or, essentially. So this is the not of an or situation, so plus being or. So the not of an or is equal to what? So it's the and of the not. That's one version. And the other version, the not of a product, or not of an and, essentially, is the or of the nots. So that's a useful property just to remember. I mean, it's true for logic sort of stuff. So it's true for trues and falses. So it is actually useful when you're doing computer coding to know that result. So it's a way of doing a not of an and or an or expression, essentially. And when you do the not of an and or or, it swaps from or to an and, or an or to an and, etc. So to prove this, I'll just do the first one. So essentially, what we want to try to do is we're trying to prove that x plus y
So we're trying to prove that the complement of x plus y is x bar dot y bar. That's what we're trying to prove. We're trying to prove their complements to each other. So what we need to do, hence we need to show, so to prove anything is a complement really is to prove that if you take the sum of them, you should get 1. First thing you need to show. And the second thing we need to show is that if you take the product of the two, you should get 0. That's the definition of being a complement. So that's the easiest way to prove complementary stuff. So you can use proof de Morgan's law using Venn diagrams, truth tables in their appropriate spaces, but how to prove it in general really revolves around proving both those two results there. So that's an important thing to remember. So proving complements really is just about proving these two corresponding results. So let's try to do the first one. So you got x plus y plus x bar dot y. So we're going to try to simplify this down, which looks like the hardest of the ones that we've got around. So again, it's x or y or everything else, essentially. So I want to try to group things together. So I hope this is not the wrong way of doing it. So I can do an x plus 1 plus y plus x bar plus y bar. Maybe my arrays are working. Probably stuck a 1 in there. So what I'm trying to do is I'm trying to absorb some of these terms together, effectively just to give me my 1. So the 1 can be written as y plus y bar. Expanding it out. So expanding it out. So basically what I have to do is just try to split this term up just so I've got these terms combining sort of together. So I can see these two terms are going to combine. So both have a y bar, so I can sort of factorise that y bar out. Maybe I'll write it in a proper way. Plus x dot plus x bar outside of y bar. So I can sort of factorise the y bar out. That's the whole reason why I did that. So I split a term up just so I can combine it in a different way. What's the x plus x bar equal to?
0. Sorry, 1.
1, yep. I feel like I've dropped something here. Yep. That's better. So basically the x plus x bar is 1, so it sort of cancels out. And again, the same thing, the y bar plus y will give you another 1. And 1 absorbs anything else, and so that's equal to 1. So basically how I did it, I mean, once you expand, so the hard step is to come up with that one. It's always hard starting these things, I find. So how I did it, I go, well, I really want to just be able to combine some of these terms together to start getting some simplification. But I really had to do that by splitting up the x into 2 parts, essentially. So in terms of a Venn diagram, so I had x and y, really I have to split up x into 1 part, so x not y, and the other part, this one here, which is the other, so x and y. So I have to split up into two separate parts of it. And once they're separated into two parts, then I could simplify the rest of it down. That was the basic trick I did. So the other case, I have to do the x plus y dot x bar dot y bar equals 0. That's what I'm going to prove. This one's a bit easier. So to prove this one, really just it means expanding the brackets out. So it's going to be x dot x bar dot y bar plus y dot x bar dot y bar. That's expanding it out. What would you do next? So I'm trying to make it equal to 0. That's what I'm hoping for.
X and not x is 0. And then
Yep.
Y and not y is also 0, so you're left with not y or not x.
So these two terms together, so y and y bar, would give you 0. That's right. So you're getting x not x and the y not y. Both of them just going to collapse down for you. And 0 in anything, 0 absorbs once you get 0. So that one fell out pretty quickly, fortunately. And so doing both of those, and again, you could change all this just to set notation if you wanted to. You could just change multiplication to intersection, the pluses to unions, complements to complements, etc. And it would work the same sort of way. So this is a more direct, much more clear approach if you want to set it for anything else to that matter. Okay. So as you've noticed, apart from that last one, apart from this double complement role, all the other ones form in pairs. All these results have pairs to them. And so we call the pairs joules of each other. So how you find a joule is basically, when you write a roll, you just swap if you just go to swap plus and multiplication, or in terms of logic, swapping ands and ors, or swapping intersection and unions, they're all the same thing. So just swapping those two operations around, and if you see a 0 and 1, swap those around as well. So you got x plus 0 equals x, for example. The joule of that would be replace the pluses by multiplication and you replace the zeros by ones. So the joule of the first roll is that second one. So that's what the idea of a joule is. So just swap pluses, multiplications, zeros and ones. Everything else stays the same. So complements would stay the same, for example. That's the idea of a joule. So if you look at some of these proofs, like that proof there, for example, in order to prove the dual result of De Morgan, so the other version of De Morgan's law, I could take the dual of every single line and it'll prove my other result for me. So, which I'm not going to bother writing down, but that shows you that if you can prove one result to be true, then the dual result will automatically be true as well. So for all these examples, I've only proved one of the cases, not both of them. And the reason for that is because they're dual results. So the key thing here is the duality principle. If you've got a statement which is true in a Boolean algebra, then its dual is automatically true. Read for you. And so you don't really need to prove the other one at all. So let's try this example. So x dot 0 equals 0. I don't think I proved that one, did I? I did. So I proved that one earlier, so we don't have to do it again. What's the dual for that statement?
X plus 1 equals 1.
Yeah, x plus 1 equals 1. And what's the proof for that?
1 absorbs the x.
Okay, so the proof is, I proved the first result earlier, therefore it's true because it's a dual. That's it. I mean, you could explain it, what you're saying. I mean, the answer is because 1 absorbs anything, that's right. But in terms of having to prove the result, you have to say, I've proved the first result about 20 minutes ago, whatever it was, and therefore the dual is automatically true. So you don't actually have to prove it. So understanding duality is important. So as in everything comes in pairs. Almost everything comes in pairs. So occasionally results are self-dual, which means it's the same thing. Didn't come up properly. Okay. So what I want you to know, for your exam, is I want you to know there are a few different implementations of Boolean algebras, and you need to know what they are. So you need to know how to prove some results in Boolean algebras, so a bit like what I've been doing today. You also need to be able to simplify Boolean expressions, so something like this one here, for example. So this is a Boolean expression.
It's actually y. It's y.
So I would like to work out how to simplify these things. So there are two different ways of, I want to show you how to do it. One is to use the results, and one is to use Carnot maps. So the two things I want to try to show.
You mean Cambridge?
Maybe they're the same thing. But so I always know them as Carnot maps, named after the guy. Maybe they're K-maps for sure. We'll see if they're the same thing when I write them down, I guess. You can let me know if there's another name. So, in order to simplify this expression, we need to be able to use... Let's try to use the results to begin with. So, in order to do that, how do you simplify this down? What was the first thing to do to look at this to try to simplify it down? So you jump straight to the answer like Jacob did, but let's try to do it step by step. What steps would you do to try to simplify it?
De Morgan's on the first bit,
Okay.
so you get y and not x.
Yep. So using De Morgan's and double complement.
Yep. And then on the next bit, straight away you got two y's, so you can just simplify that down to x and y.
Yep, which is the idempotent property. I'll give some names here.
You can take the y's out to get y and x, or not x.
Yep, so we factorise the y out.
And then the x or not x cancels out to be 1. You're just left with y.
So x plus x bar is the complementary property. And then that's the identity property. Give me some names for them all. How do you remember the names? You're allowed a formula sheet in your exam, so you're allowed to have them on the formula sheet if you wish. So the example formula sheet has those rules written all down.
There will be a question, and it says you need to write what you're doing, won't you, for each step? Yes.
You need to have some working, yeah.
Yeah. So you can't just like do the working. You got to write what property you used.
So in the assignment, like it was a question like this in assignment 1. Yes, you had to write stuff down. In an exam, sometimes a little bit more generous with the marking and that sort of stuff. You do need to, I wouldn't accept just saying equals y for 4 marks. I would have liked some working.
Yeah, the working. But my question is, do you need to have the property that you used written down with the step?
I can't remember what I decided. I've put the marking scheme already down. I have written it, as in, for these things in the exam, a question like this in the exam, I wrote down what I wanted on the exam script. That's what's going to be the guide. And I just can't remember what I wrote down. So you'll find out when you read the exam.
Great. Just what I needed.
So there's a 50% chance you'll need to know the steps that you're doing,
Well, you need to know what steps you're doing.
or you need to know what they're called.
But that's easy. Just look up in the form sheet what the name is. That's all it's through. if that's what's required, just look up the name. So the most important, some of them are not surprising at all, like being able to reorder stuff and moving the brackets around. Those you sort of take for granted. That's the associative and commutative properties. But the ones that you really have to remember are things like De Morgan's rule, and knowing the name of that one when you're using it is useful. Just to realise I'm actually using it. So I'm not look. At the end of the day, I want to know if you can do the simplification more than anything else. So if you miss one or two, I'm not going to penalise for that, but at least you have some effort to show working essentially. So that's the first way. So another way is to use the idea of a Carnot map, which is named after Mr. Carnot. And the way to do that really is to work out the truth table first. That's the first thing you want to do, is to work out truth tables for a function. So you got x and y, so we've got 0, 0, 0, 1. So work out a truth table for this sort of expression. And it's just easy to just plug some values in. So if you type in 0 and 0, you get nothing, just plugging in or plugging away. So I'll just do it quickly.
1, 0, 1.
Yeah, so the rest is sort of cheating immediately. I did actually do it for 0 for the first one properly, but so you get the truth table, work out the truth table for these things. So any function at all is defined by its truth table. And you can work the whole thing out by just subbing in. Slowly if you require, but you get the truth table. So how Carnot maps works, for two variables, essentially you just draw a grid, and on the top you draw all the different values you have for y, and the columns you have all the values for x. And then you just write down the values for the truth table in the diagram. Have you done these things? This is the K-map you're referring to. So we had, when x and y were both on, we had a 1. So that corresponds to that value there. When x was on, y bar, when y was off,
We had 0.
we had a 0. The other way around, we had a 1. And when both were off, we had a 0. So you put the zeros in, or you can leave the zeros completely out if you wish. So that's the corresponding Carnot map for this truth table. Then, in order to work out the most simplified expression for this, basically what we do is we cover the map with blocks. The blocks have to be of size 1, 2, 4, 8, 16, etc. Depends how many variables you've got, how many you can go. If you're trying to find the biggest blocks you can. So in this case, the biggest, there's only 2, and you just want to cover all the ones, only the ones. So the biggest block you can do in this case really is just covering up just those 2 ones. That'll be it in this case. And then each block of this size 1, 2, 4, etc. has a simplified expression. So since in this case I colour the whole column y in, this would correspond to the expression just y. And so the original expression is equivalent to just y. That's the most simplified way of writing it down, which we've already worked out middle. Now for 2 variables, you probably can work it out yourself. But the same technique generalises to 3 and 4 variables nicely as well, which I'll do in my next lecture. But just a few more expressions. So if we had that Carnot map, for example, what expression does that simplify down to? So again, you try to cover it with the biggest blocks you can. Unfortunately, you can't cover it with much. So you can't. There's no 4 blocks you can cover it with because not all ones. You can't even cover it in 2 blocks. So you really are forced to cover it with 2 1 blocks here. So basically, what you do is you work out the expression for each one. So the expression for the top left corner
would be x and y. And the expression for the bottom right would be x bar, y bar. And once you get the expressions for each part, you add them together. So that would be a simplified expression for that. Which is essentially, we've written it before, x is equivalent to y, or x equals y effectively is what it corresponds to. So that's might be natural way of writing it in other symbols, but in terms of just ands, alls, and nots, you really are forced to write it down something like that. So one more example. So that sort of truth table there. Again, we want to cover it by the biggest blocks we possibly can. So what blocks would you cover this one by?
X or not Y.
So you cover it by that whole column or that whole column. And so the row that covers all the X column would be X. The one that covers the Y column would be Y bar. So that would have been my simplified expression. So I'll do the three variable case in my next lecture, but it's a similar sort of idea, except you're allowed to have there be 8 squares you want to kind of cover, and the harder bit is it wraps around. So the trickier part, but we can handle it in a second. So it's a good technique to try to simplify expressions down. As I said, it's a bit overkill for 2 variables because you can work out directly because you probably know them familiar enough, but it's good for the higher order ones. We'll finish it there today, but we'll do some more simplification in the next lecture and do logic circuits, and that'll finish up with the theory you want to do, and then any time spare we'll do revision after that. But we'll do tutorial this afternoon on the 12, that is, on recurrent relations. Yep. So see you guys then.
You are currently the only participant in the conference.